Bismillahirrahmanirrahim. Assalamu alaikum everyone. So today we will be having our 14th lecture and we will be talking about binary adders and subtractors, right? So whenever we talk about the digital systems, they have to perform certain mathematical operations, right? And one of the important operations in those arithmetic or mathematical operations, that is addition and subtraction, right? So let's start, right? So these are the bullets which we will be going through one by one, right? We will be talking about addition, then subtraction of binary numbers, right? And then how we will be handling carry, right? Because this is important. If we are adding two numbers, how we will be handling carry, and if we are subtracting two numbers, then how we will be manipulating the two numbers, right? Subtraction, right? And then if we talk about the addition, right? So it's rather easier to add two numbers, right, on papers, right? But we need to have a circuitry, a hardware, in order to automate this addition and subtraction operation. So ultimately we will move forward towards the hardware implementation, right? So we will start from the single bit adder, right, and then we move on and we will be having adder with more than one bits, right? Then there is another problem, right? Whenever we talk about the addition or subtraction on a piece of paper, so what normally we do, if we have a carry, right, we place the carry at the top of the two numbers that has to be added or has to be subtracted, and or in case of subtraction, right, we normally borrow something, right? So this is easy to handle on piece of paper, right? So what we will be doing when we have a carry, right, that is not equal to the number of digits or number of bits, right? So for example, if we have the resultant, right, that is more than the number of bits or the number of digits we are going to add, right? So that sort of situation we have to handle, right, or we have to manipulate. So we will be talking about overflows, right, and like what happens, right, when there is a situation of overflow and how we can handle that situation, right? So let's start with the half adder, right? So we will be starting from the single bit, right? So if we have two bits, right, and we have to add those bits, right? So here we have the sum, right, represented by S0, right, and we have represented the two bits that has to be added by A0 and B0, right, and C1 is representing carry, right? So two bits, right, and you know that we can have four different combinations, right? 0 0 0 1 1 0 1 1, right? And if we talk about the sum, we all know that the 0 0 sum is 0 and carry is 1, right? 0, and 0 1 sum 1 carry is 0, 1 0 sum 1 carry is 0, right? And here we have a very different situation, 1 1, right, and we have sum 0 and we have carry 1, right? So if we talk about the binary and decimal addition, right, so here you can see that we normally have 2 in decimal, right, or here we have 1 0. If we talk about the weight, so 2 raised to power 0, so this has 1, right? Here we have 2 raised to power 1, it is carrying a weight of 2. So what we will be doing, right? So if we talk about, so this is 2 raised to power 0, 2 raised to power 1, right? So what we will be doing, 0 multiply by 2 raised to power 0 plus 1 multiply by 2 raised to power 1. So 2 plus 0, this is 2, right? So this is the decimal equivalent, right? So let's move towards the circuit design, right? So here if we are having 2 inputs and 2 outputs, so we will be having or designing the circuitry for each output individually. So let's talk about S0, right? So if we look S0, in this column we have 2 ones, right? 1 1, right? So if I am interested in the min terms, so I will be having, this is M1, right? M0, M2, M3, 4 combinations. So what I will be having, A0 bar, right? B0, right? And A0, B0 bar, right? So I will be adding them, right? So if I will A0 bar, right? A0, B0 bar, right? So this is what? This is the conventional XOR operation between A0 and B0, right? If we talk about the sum, so we have only one, right, at the last, right? So here we can have only one term, so this is A0 dot B0, right? So we have A0, right, B0, so here we have A0 XORed with B0. So this is the sum and carry. But remember that here we can only add 2 bits, right? So here what is different, we have the carry and the sum, right? So what happens, right, if we have to add more number of bits? So let's assume that we have 2 numbers, A, right, it has 4 bits, right, and B, it also has 4 bits, and we have to add those numbers. So if we talk about the addition on a piece of paper, so what normally we do, because we have already learned about the binary addition, so we will place those 2 numbers in this way, right, A and B, right, and then we will start the addition bit by bit. So here 1 1, we will get 0, right, and carry will move here, right, 1 1 and carry will move here, right, and then we have 1 1 and again carry will move here, right, again carry will move here, right. So we will have the sum, right, so this is S0, S1, S2 and S3, right, right. So and if you talk about the carry, so we have C0 here, C1 here, C2 here and C3 here, right. So you can see that the movement of carry, we move the carry, right. So we got the carry here and we have placed it here one position ahead, right. So if I have to represent that scenario, so we have a carry, we have the corresponding bit from A and the corresponding bit from B, and I have the sum and I have placed the carry here, right. So each bit, it is creating a sum and a carry, right, and we have to place that carry one bit ahead. So if I have a carry here, I will be placing it over here, right. So now we have a truth table, right. So we actually are interested in designing a adder circuit that can perform the addition regarding more number of bits, right. So here we have taken 4 bits, right. If I go back 4 bits, so So I will be having Ci, Ai, Bi as inputs, right? If you look here, so these are the inputs, right? And then what I will be having a sum and a carry, right? So sum and carry, right? So but carry is from the next position, right? So here you can straight away calculate the addition, right, represented by S, and then we can also have the carry, right? So 0 0 0 0 0 carry, right? 0 0 1 1 sum and 0 carry, and here we have 0 1 0, right? So we have 0 sum and 1 carry, right? And then if you look here, we have 1 sum and 1 carry, right? So what I will be doing next, I will be plotting this onto the K-map in order to have simplification, right? So here, if I talk about the min terms, right? So here I have M0, right? M1, M2, M3, M4, M5, M6, M7, right? So I have a 1 here, so I will be having Ci bar, right, Ai bar and Bi, right? So here I have Ci bar, right, Ai, right, and Bi bar, right? And I have a 1 here, right? So that is Ci Ai Bi, right, here bars, right? And here Ci Ai Bi, right? So what I will be doing, so for sum I will be doing, that is equal to what, right? Ci Ai Bi, right, plus Ci Ai Bi bar, right? And then we have Ci Ai bar Bi bar, right, plus Ci Ai and Bi, right? So and we can also straight away map those ones, right? So here we have Ci bar, right? Ci bar Ai Bi, right? If I talk about this, so this is what? So this is Ci bar, right, Ai bar, right, and Bi, right? And then Ci bar, right, Ai Bi bar, right? And then here we have Ci Ai bar Bi bar, right? And here we have Ci Ai and Bi, right? So we can also, moreover, you can see that we cannot simplify it, right? Because we don't have any pair, right? So that even after the banding or twisting, we don't have any pairs, right? But if you remember, we can straight away write down the simplified expression by using McCluskey mechanism, right? So let me write down, right? So we are having Ci common, so here Ai Bi plus Ai Bi complement, right? So plus Ci common here, right? Ai bar Bi bar, right, plus Ai Bi, right? So if I start here, right, so Ci bar and AI XORed with BI, right? So here plus CI A plus BI whole complement, right? So if I replace I have to replace this AI plus BI XORed, right? So CI X plus CI X bar. So this is what? This is CI XORed with X, right? So what I will be having CI plus, so this is the resultant regarding the sum, right? So this is the same, and this is sum. You can see that we have the same simplification, right? And this is the representation in sum of the products, right? If you talk about the sum, so the only difference is there that we have handled the complements externally, and here we have named the inputs differently, right? So let's move to the carry, right? So if you see here, right, again we have to place right here M0, M1, M2, M3, M4, M5, M6, M7, right? So let me do it differently, right? M0, M1, jump, right? M2, M3, right? M4, M5, we have to jump, 6, 7, right? So you can see we have one here, one here, one here, and then one here, right? So M1, M3, 1, right? And then we have M5, 1 here, M6, 1 here, M7, 1 here. So now I will be looking for the pairs or groupings, right? So we have a group here, this pair, right? And then this one can be reused. So I have a group here, I have a pair here, so I can reuse this one so that I can have maximum simplification, right? So what we will have, right? So if I talk about this, right, this grouping, so what we will be having, CI will be eliminated, right? And what I will be having, I will be having AI BI, right? And if I talk about this, right, so for this I have CI, right, and what will be eliminated, BI, AI will be eliminated, right? If I take this pair, right, so I will be having CI and AI, right, because B will be eliminated over here. So we have 3 groupings and we have 3 terms for carry, right? So this is the way out, right? So you can see that we have, but I want to represent this expression in such a way so that I can transform this into the XOR operation, so that I can reuse the XOR that I already have seen regarding the sum, right? So here I have represented the carry in some of the products. So you can see that we have 2 levels, right? And we have 4 gates, right? So sum of the products, right? So then what I did over here, I have the carry, right? So I will be converting or transforming that Boolean expression so that I can reuse the XOR operation. So you can see that we have AI BI, right, plus CI into AI bi plus ai bi bar, right? So here I can take ci as common, right? So here you can see this is what, this is the XOR operation, right? So I can now reuse this XOR operation. So ultimately my objective is to design the hardware, to design the circuit for the sum and carry. So that is the full adder circuit, right? So if you look here, right, we have a sum and we have a carry, right? So here also we have a sum, we have a carry, right? So it means that what I did over here, I have cascaded two adders, right? Sum, right, and carry. So I have cascaded two half adders, right? So those are the two half adders, and you know that the half adders, they can only add one bit, right? If you talk about, if you go back, right, so this is the half adder, right? So it can only add 2 bits, right? So but I have a expression over here, right? So you can see that we can cascade two half adders, right, in such a way that it can add. So this is the full adder, right? So you can see that we have the carry, right? Okay, now so this is the block diagram. You can see that the two half adders are cascaded and we have the full adder, right? But the problem over here is this even full adder can only add 2 bits, right? So I have to do something else in order to have a full adder for 2 binary number addition, right? If I have a 4-bit binary number, right, and I have another number, 4-bit binary number, and I have to add them, so this full adder cannot do that because it can only add 2 bits. So you can see that we have 2 bits, right? This is the carry in, this is the sum, and this is the carry out, right? So this cannot do the job regarding the binary addition of more than 1 bits, right? So what I have to do, right? So I have to connect number of full adders, right, in this way, right? So this is, you can say, a 4-bit adder, right? So here you can see that we have a full adder, right? So this is the carry in, carry out. So this carry out is the carry in for this full adder, right? So here this is carry out and this is the carry in for the next adder. So you can see that the carries are moving like a ripple effect, right? So we have to add these 2 bits, right? So we will be having a sum, then the carry has to be fetched to the next adder, right? So then what we can have, right? So then we can have this is the carry in, right? So this is the same. If I write this, right? So here I have A1, B1. So this carry is moved here, right? Right? B1, right? And then we move on, right? So here I have 2 bits, corresponding bits, right? B2, and the carry is moved here, right? So you can see that we are actually having the chain of full adders, right? And we can add 4-bit number. If I need a full adder, right, that can add 5 bits, so what I need to do, I have to add one more adder. So I will be having A4, B4, and then I will be representing S4, and similarly carry out as C5, right? Right. So let's talk about the 2's complement, right? So if you talk about the subtraction, right? So subtraction is almost addition for us, right? So how? So what normally we do, I have to subtract two numbers. So I place a bar to represent the subtraction, right? So this is again very easy on a piece of paper and you can subtract straight away, but whenever you talk about the system or the digital circuit, so you have to handle these things in a systematic way. So what I will be doing, so this is actually if this is A and then this is B, right? After, so what I will be doing, so I will be taking 2's complement of this number, right, and then I will be performing the addition. So how we can normally take the 2's complement of a binary number. So for example, if I have a number here, right, so I will invert all the bits, right? So this is what, this is 1's complement, right, and then I will be adding 1, right, 0, right, 1 carry, 0, right, 1, 0, right. So this is what, this is 2's complement. So now what I will be doing, right, so this is the number and I can say this is minus B. So what I will be doing, I will be doing this, right. So I will be actually performing the addition, but I have the 2's complement that represent the negative of that number, right. Okay, so let's talk about the subtractor, right. So here you can see that we have the same representation or same circuitry of full adders, right, chain of adders, right, and there is a change, like you can see that we have introduced XOR gates, right, at the input of number that has to be subtracted, B, right. So and we have a control signal, right, E, and this control signal is fetched here as a input carry, because if we talk about this, so you cannot have a carry even, or you cannot have a carry before starting the addition, right. So we always place a 0 here, right. So this is the same, like if you have a 4-bit number 1 0 0 0, right, 1 1 0 0, this is A, this is B, and you have to add them. So we don't have a carry here, we have a 0 here because we have not started the addition. So here we have 0, right, and if we have a carry here, then that carry will move on, right. So this is the way out, right. So in that case, what we did over here, we have a carry, right, even we have not started the addition, right. So what will happen, so let's say I have a number here, right, A is equal to 1 1 0 0, right, and B that is equal to 0 0 0 1, and I have to take the subtraction, I have to subtract A from B, right. So let me place the, so this is 0, right, this is again 0, right, again 0 and 1, right. So I have to perform the subtraction, right. So what I will be doing, I will be putting E is equal to 1, right. So E1, so we have a 1 here, 1 here, right, 1 here and 1 here, right. So all ones because E is 1. So remember that we also have a 1 at the carry in at the position of the first full adder, right. So we have a 1 here, right. So what happens, right, so 1 1, we know this is what, 0, right, because XOR is always 1 sensitive, either A high or B high, right, but not the both. Here we have both high, so 0, so this is 1 sensitive, so 1 will be passed, 1 will be passed, right. right? So if I take the complement of this number, so what I will be having 1 1 1 0, and here if you look 1 1 1 0, so this is 1's complement, right? So this is 1's complement, right? Okay, and what is the next, right? So here if we have a carry here, right, so that carry, right, so that carry will be added, so it means what we will be doing, right, 1 1 1 0, this is 1's complement, and I have to add 1 1 1 1 1, right? Right, so this is the 2's complement, because if we add 1, and we have to add 1, right, at the least significant, right? So this is 2's complement, right? So now I have minus b, right, and what I can do, I can now perform the addition, right? So the rest of the operation is the same as the addition. So due to this arrangement we can have subtraction, right? So you can see that a to the b, 1's complement plus 1, right? So this is always there, right? So we can have the difference represented by d0, d1, d2, d3, right? Okay, so this is the adder subtractor circuits. If we have a 0, if I place 0 over here, right, let's talk about the 0, right? So if I have a 0 here, right, so what will happen, right? So let me place the zeros here, 0, right, 0, and what we have at b, right, 0 0, this is 0, this is 1, right? So this is 1, I place here, this is 0, and this is 0, and here we have 0, right? So you can see that if e is equal to 0, we have the same number, and now we will be performing the addition. So this is the difference, right? So here this is the adder subtractor circuit. The only thing you have to do, you have to make this 1, then you will be subtracting. If this is 0, then you will be performing simple addition operation, right? Okay, so let's talk about the overflow, right? So whenever we have two numbers, binary numbers, for example a and b, and we have 4-bit binary number, right? Right, I have making the bins for those numbers, right? So let's talk about so I have to add, right? So what will happen? 0 1 carry, right? 1 1 0 1 1 carry, 0 1 carry, but I have 4 bins, so I cannot store this extra bit, right? So in that scenario, what I will say that now we have the overflow situation, right? And we have to handle that situation, right? So here we have another example, right? If I talk about this, right, I have to represent -3, right? So how I can represent -3? This is 1 1 0. For sign bit I place a 0. So what I will do, as we know that we take 2's complement, 1 0 0, right, and then we add 1, right? So 0 1 0, and this is the sign bit. So this is the -3, right, -3. And then if I have to represent 6, let me -6, right? So I have 1 for sign bit, right, 4 2, right, and then this is the inversion, right? This is 1's complement, right, and this addition will make it 2's complement, right. So I will be having 0 1 0, and this is the sign bit, right. So what I will be having, right, for this 6 we have 1 0 1 0, right, and we have a mistake here, so right, 3. Okay, so we did it wrongly, right. So what I will be doing, 3, so 2 plus 1, so I will be having 1 here, 0 here. So in inversion I have 0 0 1, right, 0 0 1, right. So 1 0 1, right. So 1 1 0 1, so this is minus 3. So if you look, right, so we will be having minus 9, right. So if I talk about minus 9, 1 for the right negative, and then I need 4 bits, right. So and then overflow has to be certain, right. So here we will be having a overflow, right. So if you talk about this overflow, right, so here we have a 3 and we have a 6, right. So normally what we have 3 plus 6 9, so I need more than 3 bits. So for 3 I have 0 1 1, and for 6 I have 1 1 0, right. So what will happen, 0 0 1, right. So this is what, this is the sign bit, right. I have to take the complement, 1 1 0 plus 1, so 1 1 1, this is the sign bit, so this is what's minus 7, right. So this is again wrong, right. So we should be having 9, but instead of 9 we are having minus 7. So here instead of minus 9 we have 7, right. So these are the overflow situations, right. We can also have the examples like this, right, 70 80, right. So you can represent, this is the sign bit, right, and you can see that we are having the negative sign. This is 1, this is showing that we have a negative sign. So because 0 means positive, 1 means we have a negative, right. So here again we have negative numbers, so we have a 0 here, right. But in the true answer we should be having minus 150, right. So these are the overflow situations, right. Then let's talk about the ripple effect, right. If you talk about the adder, you can say that this is a parallel adder, right. And if we want to manipulate or handle more bits, we need to add more adders in parallel, right. So here if you have to have n bit numbers, right, then you can have n full adders in parallel and you can cascade them, right. So here you can see that this is the carry in, right, and this is the carry out, and this is the carry in for the next one. So there is a sort of ripple effect on the as the carry moves on from the least significant bit to the most significant bit. So you can feel a ripple effect, right. Okay, and then there is another problem, right. If I go back, so if we know that each gate, it introduces some propagation delay, right. If this has some amount of propagation delay, then that delay has to be moved here, right, and then that delay will be keep on adding up till we have reached here, right. So if we start from here, right, so this has the delay, right, and then this will again having more delay, so it will be having a ripple effect, right. So we have to handle this, right. So what is the solution? So what we can do, we can design a circuit that is called a carry look ahead adder, right. So what the objective over here, right, so we have to reduce the propagation delay, right, and what we can do, we can have the carry look ahead adder circuit. So you can see that in normal addition we have two numbers, binary numbers, and we have to place the carries at the top, right? So you can see here we have a carry C0 at the 0th position, here we have a carry as first position, and so on and so forth as we move on, right? And we have a sum here, right, as we go on, right? So this is the same full adder circuit, right? But what we did over here, we have tagged a propagator over here, right, PI, and then the generator over here, right? So you can see that this is the internal signal, right, PI, and you can straight away compute, or you can straight away calculate its output, right? AI is ORed with BI, and generator is AI ANDed with BI, right? So carry generate, right? So Ci plus 1 is equal to 1 when G is equal to 1 regardless of the input carry, right? So Gi will be 1 irrespective of the input carry, right? Then if you talk about the propagator, right, so ultimately it has to propagate, right, Ci to Ci plus 1, right? If you look at the propagator, so Ci has to be propagated to the next carry, right? So here we can realize that PIs and GIs, they depend only on AIs and BIs, not on Cs, right? So what we can do, right? So these are the representations. Si, this is the input, and this is the output. This is the intermediary Boolean expressions, right? So you can see that we have Ci plus 1 is equal to Gi plus Pi Ci. So what we can do, right? Right? So C1, right? If I place a 0 here, right? So C1 will be equal to G0, P0, C0, right? C0. You can always say C0, right? Then C2, obviously we have placed 1 here, so we will get C2, right? And this is equal to G1 plus P1 C1, right? And here we have a C1, right? And we already know the C1, so we can place C1 here, so we will get G1 plus P1, right, into G0 plus P0 C0, right? So here you can see that we have represented, right, C2 in the form of G's and P's, right, and C0, right, not the C1. C1 is not there, right? Similarly, if we have the C3, you can see C3 is represented by P's and G's, right? C0 is still there, right? So if we talk about the carry propagation, right, so in C2 there should be C1, right? In C3 there should be C2, right? Right? So but here what we did something different, that we have converted that C3 in such a way that it is only depending upon P's and G's and C0, that is the carry at the starting position, right? Similarly C4, right? So this is the sum of the products regarding the look ahead carry generator, right? So you can see that we have a 2-level circuitry, right? And but what we learned from this look ahead carry generator, like, right? So you can see that each carry bit can be expressed in the terms of C0, right, and P's and G's, right? There are no carries, right? Like if you talk about C3, there should be a C2, right? But we have replaced them, right? And each carry bit can be expressed as a sum of the products and can can be implemented using a two-level circuit. So if you look here, you can implement this, right, by using a two-level circuitry, right, sum of the products, right. So this is the circuitry, carry, look ahead, adder, right. So as we are talking about arithmetic operations, so let's talk about the BCD addition. So for example, if we have to add two BCD numbers, right, so we have to keep in mind certain limitations, right. As we know that we can represent a decimal number from 0 to 9, so what will be the limit, right. So we cannot cross, right, from 1001, so this is 9, so you can only have the representation or even the sum that should not exceed. But this is very natural that if I have to add two binary numbers, right, 9 plus 9, so what I will be getting? I will be getting 18, right. So I also has to represent the carry. See, I've mentioned this with C. So what will be the solution, right? So what we need to do, we need to take certain correction steps in order to represent this sum, right? So let's talk about this derivation, right? So on the left hand side we have the binary sum, right? For example, if we have two numbers and these are representing the sum of those different numbers, so here we have a K as carry and here we have a C as carry, so these are the BCD sums, right? So here you can see that the two sums, they match till 9, right, 0 to 9. So this is the decimal line, so you can see that they match each other till 9, and after 9 we have to take some sort of correction steps, right? So here if you look here, so we can recognize that we have to correct, right, when we have 1 in the carry regarding the binary sum, right? But what about those 6 positions, right? 1 0 1 0, right, till 1 1 1, right? So what we need to do, right? So whenever we have K is equal to 1, we know that we have to take some correction steps, right? So for this, right, so let's have the derivation, right? So for example, if this is the sum, right, and we have to convert that sum to the BCD sum, right, because this is very natural that whenever we will be adding two BCD numbers, we will be having BCD sums, right? And in order to restrict ourselves from 0 to 9 representation, we have to add them, right, or we have to make something different. So over here what we will be doing, so let's talk about the addition regarding the two numbers. So here if you have 1 0 1 0, right, and you have to make it equivalent to this corresponding position, right? So what you will be doing, so we will be actually adding 6, right, 0 0 0, and then we have 0, right? So this is the carry. So you can see that we have the matching over here, right? Similarly, if you have to manipulate this, right, so we can always have 1 1 1 1, so 1 1 0, right, and 1, right, and then we have 0, right, 1 carry, 1, right, and 1 carry, right, 1 plus 1 1 carry, so we have a 0 and 1 here, right? So if you look here, right, so we have the same number 1 0 1 0 1, right? So this is the way out to convert, right, to have the equivalence, right? So this is the way out. So whenever we have K is equal to 1, it is understood that we need to add, right? So in that case, right, so this is the expression, right? C is equal to K plus Z0 Z4 plus Z8 Z2. If you plot those different combinations onto the K map, and after the simplification you can get this expression, right? So here is the circuitry for the addition of two binary numbers. So you can see that we have two binary numbers, right, and we have to add them, right? So this is the K carry, right? So you can see that we have K plus, right, K plus, if I have to write this, right, so here we have K plus Z8 Z4, right, and then plus, right, Z8 Z4, right, plus Z8, right, and this is what, Z2, right? So this is the output carry, right, C0 C, right, and this is the sum, equivalent sum. So we will be having the equivalent sum and the carry, right? So this is the conversion circuitry for the addition of two binary numbers, right? So this is the way out, right? So let's talk about the binary multiplication, right? So this operation we all know that is similar to the decimal operation, decimal multiplication, right? So whenever we multiply two bits, right, they will generate 1 if both bits are equal, right, and we will be having 0 otherwise. So this is very similar to the AND operation, right? So let's have the multiplication. We have a 2-bit binary number B1 B0, so it has to be multiplied with A that has 2 bits A1 A0. So you can see that A0 B0, right, then A0 B1, right, and then we have to move ourselves, right, to the next row, right? So here we have A1 B0 A1 B1, right? So if you look, right, so this is the addition operation. So here we can have carries, right? So if we think about the design, so you can see that we have the two numbers A1 A0, right, and then B1 B0, right, two binary numbers, and then here we have the carry C0, right, C1, right, and here we have the C2 C3, right, and this is a half adder, right, and this has this is sum is fetched here, right? So you can have the half adders and then you can connect them in this way in order to manipulate the multiplication, right? So that's all for today's lecture, right? So today we have discussed one of the important operations, that is addition and subtraction, and then we talk about the single bit addition, right? How we construct the circuitry from the truth table regarding the 1-bit adder, then we move from 1 bit to the more number of bits adder, right? And then we talk about the full adder, right? And then how we can have a single circuit in order to manipulate or handle the addition and subtraction. And then we discuss the overflows, right, and how we come across the overflows, right, whenever we have the addition of two numbers. So, and then we talk about the BCD addition, right, how we can have the binary coded decimal additions, right, and finally we discussed about the multiplication, right? So that's all for today's lecture, right? So मेरी तरफ से अल्लाह हाफ़िज़, अस्सलाम वालेकुम।